nanohub.org.
Just a quick introduction. Again, this is Mr. Lee Stauffer from Keithley, and he's here to be with us for 2 days. I gave you the agenda. Kind of the first day and a half is an overview and operation of the instrument, which is sitting right here. It's brand new to Burke. About $53,000 worth of equipment sitting here. So this is going to be in 61, excuse me. And Lee's going to take us through the operation of this. And then tomorrow afternoon, you can actually bring your own devices in and get some hands-on experience with it as well. So the agenda is kind of here, and I've handed it out. We would like you to sign in with just your name and email so we can keep track of who has participated in the seminar. And with that, I'll turn it over to Lee.
Thanks so much. Just briefly, my background at Keithley. I've been with Keithley Instruments for 23 years. Prior to that, I was a product engineer in a fab. Product engineer is a person who actually works with the finished integrated circuits, but they have to debug why it's not working, why the silicon's not working. And that involves parametrics, functional test, and a variety of different test technologies. As you haven't learned yet, the semiconductor industry is very cyclic. We just went through one of the worst down cycles in the semiconductor industry we've ever had. And so I had, back 24 years ago, when I was a young man raising a family, I said, boy, I really can't go through these cycles. I need a little bit more secure job. So I decided to go into test instrumentation. Turns out we follow the same cycles the semiconductor industry follows. So, the beauty is it always does recover, and it will continue to recover. A perfect example is the new phone my company just gave me. This is an iPhone 4. The technology in this phone is absolutely stunning. Anybody of my generation takes a look at this phone and goes, there are technologies here that are unbelievable. The accelerometers, the display technologies, 32 gigabytes of flash memory. You know why they stopped at 32 gigabytes? Because flash memory has sort of reached the limit of what it can do. They can't make flash any smaller. Charge-based memories are at their limit. And so that's a great area of study and characterization that we'll hopefully get a chance to talk about. So I have to start with some safety precautions because I'm required to. So I'm not going to read all the safety precautions to you, but I will point out the bottom one here. Keithley products are not intended to be connected to humans. We're for testing semiconductor devices. So what that means is don't connect this thing to your undergraduate assistant and find out if it's making voltage, okay? Because it will shock them. This can make up to 200 volts, and it's enough power that it will shock you. Here is our schedule. You certainly are welcome to participate in the parts that interest you. We're going to do an overview this morning, and then we're going to go into the Keithley interactive software, the Kite software. That's the heart and soul of the system. The hardware is the magic, but Kite is what makes it all easy to use and get the characterization that you want. After lunch, we'll talk about speed, timing, and noise settings. This is very important toward getting good results. Then we'll go into some shielding, and we'll use low current and high resistance measurement techniques to give us some examples of how to make measurements. And we'll wind up by doing some troubleshooting and some measurement tools and considerations. Now, we're going to focus today on DC IV, current voltage measurements. But tomorrow, after a brief review of some of the other tools in the system, the programming tools, we're going to get into AC impedance and CV. This happens to be a particular favorite topic of mine, and I know that I've heard that some of you are using the Keithley simultaneous CV system. My name is Lee Stauffer. My nickname inside Keithley is CV Lee. Right? So I introduced Keithley's first CV meters back in 1988, and when Mr. Keithley sees me in the hall, he calls me CV Lee. So this is a favorite topic of mine here. And then I wanted to take just a few minutes here after lunch. I just added this to the schedule. This is the new transient or ultra-fast IV. And I don't believe that Purdue has this capability yet, but I think they really will need to be getting it in the future. And we'll talk a little bit about that then. And then at the last part of tomorrow, we'll actually be able to wheel this in the lab, I believe, and connect it to devices and really see what it does. So an introduction to device characterization, because that's what we're talking about. Really, electrical characterization is performed on 4 types of devices. We have transistors, BJTs, MOSFETs, IGBTs, a variety of transistors, a variety of diodes, PN Schottky gated diodes. We have reactive elements, capacitors and inductors, and then we have resistors, a variety of resistors, linear resistors, van der Waals structures, Hall effect structures. So we really have sort of these 3 core types of devices. Now, recently there's been a lot of technical news about memristors. Are any of you doing any memristor research here in this group? You know, it's a very interesting device. Some people are calling it the 4th circuit element. Really, its characteristics depend on its initial conditions. In other words, wherever we left it, we can come back to it, and it might be in a different state. And I don't know whether this is actually a new fundamental element type. That's up for debate. But the point is, we've got a lot of research being done in this area, and we're doing a lot of testing with the fundamental characterization on devices like memristors. Now, there's 4 types of electrical characterization. With these 4 types of characterization, you can fully define any material or device. You can create a SPICE model with it. You can tell the fundamental properties of it, the fundamental electrical properties of it, and that is precision DC current voltage, or IV. This is the cornerstone of device characterization. We have 4 IV instruments, modules in this particular instrument. The second is AC impedance, a subset of which is called CV testing. The third is pulse or transient current voltage testing. And the fourth is RF testing. Now, if you think about a SPICE model, SPICE has DC analysis, AC analysis, and transient analysis. That's what these first 3 types are: DC, AC, and transient analysis. And one of the unique aspects of this instrument is the DC, AC, and transient analysis instrumentation is very advanced and very close to ideal. We can get very close to the ideal characteristics, much closer than you might get with some of your standard benchtop instruments. Now, RF is sort of a specialized realm of testing, and we've opted to leave it out of this particular seminar. We simply don't have enough time. So we're not even going to cover anything on RF testing here, not even when we get to the CV section. So where is electrical characterization used? Well, certainly when it's doing new materials and new devices, like you're doing in your own graduate research. Device modeling, it's very important there. Process development, process control, process reliability. Electrical characterization is used in a variety of places. And our seminar today will focus around this particular instrument. Although this is Keithley's flagship process and device characterization instrument, the ideas and the techniques that we're talking about here are applicable from a variety of instrumentation perspective. There are other IV and CV instruments that these concepts will hold true, but we'll focus our energy around this particular instrument. Now, this instrument has 9 module slots in the back of it. The particular version that Burke just bought has 5 of the slots filled, so there's 4 more slots for expansion. There's a built-in 12-inch high-resolution display. This is I believe it's 1000 by 768 display, but it's got a high-res external port on it. So if you have an opportunity to connect a high-res monitor, it really makes it a lot nicer to use. It has integrated in it a Windows dual-core based PC and a couple gig of RAM, 500, I think it's actually, maybe it's either 500 gig or a terabyte hard drive. So it's got a very powerful Windows-based PC built in. And it's got an IEEE 48 standard GPIB interface for talking out or talking into it if you have an external software package that you want to control this. For example, ICCAP modeling software could control this directly. There's a standard a variety of ports, USB ports, RS-232, parallel printer ports. There's an interlock connector that we'll talk about in greater detail so that you don't electrocute yourself. One of the things we found out early on at Keithley is that if you shock your customers to death, they don't come back and buy anything else from you. So, you know, we've got a nice set of interlocks and safety things on here. And of course, we have a pair of LAN connections, so you can actually tie this to a network. Often we will see this tied to an internal network, not having access to the outside world, but just an internal network. One of the most interesting things I've seen is this instrument put in an undergraduate lab where the undergraduates had access to it via the internet, and they could run their labs in the evening or whenever. They didn't actually have to be in front of the instrument to run the labs. Here's the instrumentation modules that are available. These are the ones that you have. This is our standard 4200-SMU. That's our medium power SMU. Runs from a picoamp to 100 milliamps and a microvolt to 210 volts. I believe there's 4 of those in this unit. We have a high power version which goes up to 1 amp. And we have an optional preamplifier, which it doesn't appear that you, do you know, Amr, if you've got any?
We don't have the preamplifier, but we have 2 medium power and 2 high power.
Okay, all right. So the medium and high power are good down to about a picoamp of low current resolution. The optional preamplifier can be added at any time to go down to less than 1 femtoamp DC noise. You have the model 4210 CVU, a multi-frequency AC impedance meter. It's variable from a kilohertz to 10 megahertz, and we measure from about 20 attofarads to about a microfarad or a little higher. There is the optional new 4225 PMU. This is the ultra-fast IV module. This is the transient test module. There is an optional preamplifier for this transient test module. And we also have a pulse generator and oscilloscope available, neither of which are installed in this particular instrument. Okay. So this is what the front panel looks like. I won't bore you by walking through the individual buttons, but the most important one is number 8 here, the measuring indicator. On this new instrument, it is a very bright blue LED, very intensely bright blue. When that LED is lit, there's voltage coming out of a port somewhere. When the LED is not lit, there's no voltage coming out of the port. So just keep in mind, when you look at the front of this, there is a bright blue light on the front, there is voltage coming out of it somewhere, and it's capable of making up to 210 volts. So yeah, it will wake you up better than an energy drink. Right. The rear panel is where we've got all the variety of connectors. We've got a ground unit, which we'll talk about, the instrument slots, and the interface slots, including where the keyboard plugs in. It's a USB keyboard. You can plug it in the rear of or the front. And also, if you have an external VGA monitor, it can be plugged in the back here. The important point here is all connections are done in the back, except for a couple of USBs on the front. All connections are done in the back. All instrument connections are done in the back. Okay, system overview. The system is actually quite sophisticated, but very easy to use. You press the on button on the front, it powers up, you log on, and it will automatically load a project and be ready to test. Now, the log on is either a standard user log on or an administrator log on. We have found most places don't create a unique log on for the different users. So, but I'm not sure how your system administrator will manage it for you. You can have your own unique logon, which gives you access to just your data and nobody else access to your data, or you can have a general logon. The software is the heart and soul of this system. We will talk about each of these in some detail. Kite is the Keithley Interactive Test Environment. This is the main front panel software. This is our curve tracer software, Kite. Colt is a programming environment, low-level C programming. KCON is a Keithley configuration tool. Once your system's configured, your system administrator probably will tell you you don't need to go into there, right? KIXI is the external control interface if you want to control this from GPIB or LAN. And we also have K-Pulse and K-Scope these are applications that give you a virtual front panel on your pulse generator and your oscilloscope, all right, which you don't have in this particular product. The complete reference is online on this unit. It is a PDF, searchable PDF document, very detailed. It has every application note that Keithley's ever published in it. It's a lot of information. There is a version of this software that is available for your desktop. I don't believe it's available for download from the Keithley website, but you can certainly order the desktop version and it's copyable and you can install it on any desktop. The important thing about it is that it gives you this complete reference on your laptop or your desktop available to you at any time. You also can go in and analyze software or create tests on the desktop version. Again, this complete reference is a very, very nice set of documentation. PDF searchable. I think we're over 2,000 pages of documentation here now, so you definitely need the searchable part of it. It has a quick start guide and a reference manual and every application note we've ever published. Okay. All right, the Kite software is the main software this product runs under. It's a very versatile tool. It controls any and all instrument modules that are plugged in there in a uniform user interface. That's the main tool that we'll focus our training on throughout today and tomorrow. Colt is a low-level programming language. It's Keithley user library tool, okay? And you don't have to drink Kool-Aid to use it. It gives you direct low-level control of the instrumentation from the C programming language, but we give you a nice C shell and plenty of examples. So if there's something that you wanted to do that the GUI couldn't quite handle, this would be how you would do it. We find 90% plus of people never have to get into that. We find 10% of the people just like the program, so they drop down in there for the fun of it. All right. KCON is a Keithley configuration manager. Once your system is set up, you rarely need to go into KCON, but there are some diagnostic tools in there that you may want to take a look at. KIXI is our external command interface. This is how you can program the instruments from the GPIB or from the Ethernet. This really is only useful in general for either legacy programs that people have written over the years to do their characterization. Some people like to program in, for example, LabVIEW. And so, there's a driver for this instrument, LabVIEW. You could have an external computer with LabVIEW and talk to it via KIXI and have LabVIEW control it. Good. Precision DC source measure units. This is the fundamental IV characterization tool for any device or material or process. A source measure unit, SMU, stands for source measure unit, and it's a unit that can either source current and measure voltage, or source voltage and measure current. It's either a voltage source or a current source. It depends on how you program it. So as a voltage source, we put an ammeter in series with it. As a current source, we put a voltmeter in parallel with it. Turns out these instruments actually have both an ammeter and a voltmeter connected all the time. You can choose to have it measuring both voltage and current all the time at a small penalty in measurement speed. A typical characterization will take multiple source measure units. In this case, we've got a 4-terminal MOSFET on here with 4 SMUs attached to it. All right. This means that we could, if we wanted to, and everyone has to try this at least once, has to prove Kirchhoff's current law. Right? I got to make sure that all these currents add up to 0. Everyone has to try it. Go ahead and try it. Now, the key here is automating all of these source measure units. We want these things to know what each other's doing and when they're doing it. And that's where this Kite software and this PC comes in. It coordinates the activity of all these source measure units automatically. So let's take a look at the basic specifications. We have the medium power unit, which is 2.1 watts maximum, and the high power unit's 21 watts. You can have up to 9 units in the chassis. This particular chassis has 2 of each. By the way, they are interchangeable within a test. You can have a test with 2 high powers and medium powers and whatever combination you want. There's no limitation on that. The maximum voltage is 200 volts. In decade ranges from 200 millivolts to 200 volts, full scale. The basic accuracy is 0.01% on the measurement, 0.02% on the source. 0.01% is really accurate. You rarely see a voltage source with that level of accuracy. Right. The resolution runs from 100 nanovolts to 100 microvolts, depending on what range you're on. The current range is 100 milliamps in 7 ranges, starting at the 100 nanoamp full scale to the 100 milliamp full scale, or 1 amp if you're on the 4210, the high power unit. All right. Everything's identical between the 2 units, except the high power unit's got 10 times more power, 10 times more current. All right. Basic current accuracy is 0.03 and 0.04% on the measure and the source. So that gives you 100 femtoamp resolution and 100 picoamp resolution on the highest range. If you add the optional preamplifier, small remote module, we can go down to 0.1 femtoamp. In case you can't remember, a femto is 10 to the minus 15th. All right, so this is 100 times 10 to the minus 18th. There's not a lot of electrons in that current per second. So let's take a look at the specifications. Everyone struggles a little bit with what can I actually measure? What do the specs mean? So let's just choose the nanoamp range, which, by the way, we can do up to 210 volts on the nanoamp range with either source measure unit. The resolution is 3 femtoamps. The measurement accuracy is 0.05% plus 100 femtoamps. So this is a gain number. This is an offset number. We have a gain and offset specification on this instrument. The sourcing resolution is 50 femtoamps with a gain and an offset. So what does this mean? Our measurement resolution on the 1 nanoamp range is 1.000003 nanoamps. That's almost 7 digits of resolution, which is about 24 bits. Remember, this is a full bipolar device. So there's 7 digits of measure resolution. The offset's 100 femtoamps. We never know better than that what we're measuring. In other words, we guarantee back to a national standard that we will measure on a nanoamp range within 100 femtoamps and within 0.05%. So if you're on a nanoamp range, you're trying to measure 100 femtoamps, absolute guaranteed accuracy is 100%. Right? We can't measure better than that on that particular range. That's our guaranteed offset specification. Right? Now our source is only about 5.5 digits. We don't source as accurately as we can measure. However, we can measure what we're sourcing. We can take the A to D converter and turn it on to the source. So we will know what we're sourcing. We may not be able to accurately control it better than 5.5 digits, but we will know what it is. And notice that the source offset is 300 femtoamps. That means, for example, if I told this to be a current source and told it to be a 0 current source, as much as 300 femtoamps might flow in or out of that I don't have control over. Right? The same applies to voltage. On a 200 millivolt range, we can make an amp. We have a microvolt measure resolution. Actually, we have 0.1 microvolt, but that's down in the noise, so we call it a microvolt. With a 100 microvolt offset and a 5 microvolt source resolution. Now, 100 microvolts is pretty small, but if you're measuring really low impedances, usually gets down to, oh, I know a good example, graphene. Graphene is an extremely interesting material. You can actually go to virtually 0 impedance. It goes to some sort of ballistic mode when you get it in a certain state. It's a very interesting material. And you couldn't measure that, if you've got 100 microvolts of offset. But what we need to realize is that the specification of the instrument holds true across its entire dynamic range. So even though we're on a 1 nanoamp range here, remember the instrument's capable of an amp. even though we're on a 200 millivolt range, the instrument's capable of 210 volts. So this 200 millivolt range is capable of putting out anything from 100 femtoamp, actually 50 femtoamp resolution, up to an amp. So this 100 microvolt specification deals with that entire spread inside the instrument. It's an error source that's built up inside the instrument. So if you're operating this instrument down at very low currents, of course, this 100 microvolt will be a very small error. And you can see in our specifications that we actually get this error down to about 25 microvolts at low currents. But the core specification says 100 microvolts because it covers the entire span of the instrument. So what is an SMU actually? Well, it's actually a combination of a current source and a voltmeter. So we have a current source with a programmable voltage limit of a 7-digit current meter, a 7-digit voltmeter, and we have the ability to force that and return it on what we call the common. So we use the word common as the reference point of the measurement. It's not necessarily ground. I don't like the word ground. That refers to the earth ground. Common may or may not be at earth ground, but it is the reference point of the measurement. In other words, if I told this source measure unit to make 100 volts, it would make 100 volts between common and force. Now, if I told it to use remote sense, it would actually attach these remote sense leads. So we have a force and sense lead on the high side of the measurement, and we have a force sense lead on the low side of the measurement. And we'll talk about that in some more detail. So, a current source, the characteristic of an ideal current source is that it is infinite output impedance. And this current source can actually get very close to infinite output impedance. If we had the preamp connected to this, it's actually, I believe, 10 to the 16th ohms of output impedance. So if you tell the current source to source zero current, it becomes a voltmeter with virtually infinite input impedance. In other words, it's almost an ideal voltmeter. So a lot of people will use it that way. That's great for measuring voltages from high impedance sources. Now the SMU can also act like a V source with a current meter and a current limit, or often called compliance. And of course we still have the voltmeter. So now we've got a V source across force and common. And if we had the remote sense leads hooked up, we actually would feed back the voltage measured here to the V source and adjust it to compensate it. That's called remote sensing. We'll talk about that in a little more detail. Now, a characteristic of an ideal voltage source is that it has zero output impedance. In other words, it doesn't matter what load you put on it, it's going to still make that voltage out there. So if you told this V source go to 0 volts, it actually would become an ideal ammeter, picoammeter, or any kind of an ideal ammeter. And in fact, you could even hook up the remote sense leads and compensate for the drops in your test leads on your ammeter. So it's an ideal voltmeter, an ideal ammeter, an ideal current source, and an ideal voltage source. Very interesting instrument. Okay. Now, for the IV curve tracing part of this is where it really starts to become a useful tool, right? We developed what we call the source delay measure cycle. Remember, this is a digital instrument, digitally controlled with an analog set of measure and source capability. So the source delay measure cycle works like this. The first thing that happens is we trigger the source to go to a source value. This is called the sourcing phase. Okay? And it takes a certain amount of time to get to that source. And then we wait for a bit, some additional time. You have control of that. And then we start an A to D conversion. This is called the measurement phase. So we have a source, a delay, and a measure phase. So when we create a sweep, we create a sweep that looks like a source, a delay, and a measure. And then a source, a delay, and a measure. So our sweep is actually a series of discrete steps on this. And you have control of those steps, you have control of those delay times, you have control of the measurements. We can do linear sweeps, we can do logarithmically spaced sweeps, we can do custom sweeps. You can put whatever values you want in here. All right? And we'll talk about all the details of what you can do with this. I just wanted to get you started on it. Remember that each step in one of these sweeps is a complete source delay measure cycle in itself. The other thing to remember is that all the SMUs, in this case 4, know what all the other SMUs are doing all the time. So I can't have this SMU making a measurement while SMU number 2 is ramping the voltage. That would be giving me a transient that's uncontrolled, not uncontrolled, but unknown through my device, and I can't do that. So using the internal software, all the source measure units are automatically synchronized. You don't even need to think about that. We keep track. We make sure no SMU is measuring when some other SMU is doing something. An SMU is a 4-quadrant instrument. 4-quadrant means if I source positive voltage and I get positive current, that's a resistor. That's quadrant number 1. And if I source negative voltage and negative current, I get quadrant number 3. The key is in quadrant number 4 and 2. These are sync modes. Now this is where a power supply can't do this. Most instruments can't do this. This is like, well, we have some electrical engineers, and you can model this like an op-amp. This will operate as a source or a sink, all right? And it's not as useful in device characterization, but, you know, for example, you might have a battery, which is supplying energy to this. This can act like a load. So it's a full 4-quadrant operation. That's automatic. The instrument automatically crosses over between quadrants. You don't have to set up the quadrants on the instrument. We also have operating boundaries. These are limits as to what the instrument can do. Remember, I told you that there are several voltage ranges and several current ranges. Not every current is available in every voltage range. We have limits. For example, on the medium power SMUs, we have a 20-volt range which maxes out at 100 milliamps. Once you go above the 20-volt range, you only have 10 milliamps available. If you go to 25 volts, you only have 10 milliamps, right? But on the 200-volt range, you've got 10 milliamps all the way up to the 200-volt range. So it's important to understand that, you know, if you're operating in a 30-volt realm, maybe some of your silicon carbide might get up to some of the higher voltages. Sometimes you can hit limited currents. The high power unit has an amp available at 20 volts, and it has the full 100 milliamps all the way up to the 200 volts. So it's 10 times more power, extends the envelope out 10 times. So this is 200 volts at 100 milliamps. That's a lot of energy. It'll definitely curl your hair if you grab a hold of that. Now, compliance is also known as a current limit or a voltage limit. Compliance says, I want to limit the amount of energy that I put into my device. So when your SMU is a voltage source, compliant limits the maximum current that can be put out to the device. It's a current limit, right? When compliance is hit, it no longer acts like a voltage source. It now becomes a current source. It's hit a current limit. It's now in a current control mode. The SMU switches over or crosses over from a voltage control mode to a current control mode automatically. Same thing applies when you're acting as a current source. If you hit a voltage limit, it switches over and becomes a voltage source. Now, we recently had an interesting interaction with a memristor researcher who wanted to current limit his memristor. He wanted to ramp the voltage until the memristor changed states, and then he wanted to current limit it. It went from a high resistance state to a low resistance state, and he didn't want it to break, so he turned the current limit on. What he didn't realize is this current limit has a bandwidth to it. So the bandwidth is it depends on a variety of settings, but it can be from tens of microseconds to hundreds of microseconds before the current limit catches up. Well, this was a small memristor device, hundreds of microseconds. The device was vaporized by the time the current limit caught up. Additionally, you've got some residual capacitance in the cables that has to dump when the device switches. So this current limit for traditional devices works just fine. 100 microsecond response is orders of magnitude faster than what you might see from a traditional power supply, but hundreds of microseconds, you need to be able to calculate how much joule energy your sample can actually take to see if the current limit is going to protect you or not. This is just an example of using the load line to describe a current limit. In this case, we have a resistance of 2K ohms. We can ramp the voltage up to 50 volts. It'll max out at 25 milliamps, and it will never hit our current limit. But if we had an 800 ohm and tried to ramp it to 50 volts, it would peak out at a 50 milliamp current limit that we set. In other words, it would never get to 50 volts. Okay? The current limit's 50 milliamp. The SMU became a current source and limited the voltage to 40 volts. So here's a little tip for you on this instrument. This is something many people miss. When you set up the instrument, and I'll show you a screen to do that later, you can tell it, I want you to return to me the amount you think you're sourcing, in this case 50 volts, or I want you to actually go out and use the A to D converters and measure that. So if you actually measure what you're sourcing and you hit current limit, you will get the proper value back. But if you hit current limit and you just told it, return to me what you think you're sourcing, just the source array, it will actually tell you it made it all the way to 50 volts. It won't report. And so you'll see your current rise up and clamp all of a sudden, and your voltage appears to continue to rise. You go, why did my current clamp? Where did this come from? How did this get to 50 volts? But that's not real voltage. It's just an artifact of what you're measuring. Local versus remote sensing. This was a concept first developed by Lord Kelvin back in the late 1800s or early 1900s. So it's often called Kelvin sensing, and it basically works like this. If we have a voltage source at an ammeter, and we force out of our high terminal through our resistor, and the returns to our low terminal, then we are going to measure the current through the whole loop and the resistance through the whole loop. But if we take and we put a high impedance voltmeter and run separate terminals out here, we can measure just the voltage on our sample. We don't care about the voltage that's dropped in our test leads. So for example, if I have a current source forcing voltage out here through my resistance of my test lead, through my device, through my resistance of my test lead back to my common force, then what my voltmeter will measure is the voltage here at these terminals, labeled VM, but it's not telling me what the voltage at the device is. I have a voltage divider here. So I really don't know what voltage I have across this device. This is called a local sense measurement, and it doesn't compensate for drops in the leads. But if I take these sense terminals, in this case, sense high and sense low, and I connect them out to the device, I still have resistance in my sense leads. This call, for our purposes, we'll say the resistance in the sense lead is the same as the resistance in the source lead, RC. The difference is I have no current flow in RC. This is a high impedance voltmeter. since I have no current flow here, I actually measure the voltage here is actually measured properly here. Now I actually know the voltage out here at the device under test. And in fact, the source measuring unit actually has a feedback loop between this voltmeter and the voltage source, in this case, the compliance, so it can tell it what is the real voltage out at the sample. Now, in the early days of source measure units, this was when I just started at Keithley, right? This selection between force and sense was a manual selection that the users had to do. And so we would get users who would say, well, I want you to be a 4-wire sense instrument. But then they'd forget to hook up the sense leads. And they'd say, okay, go out and make 1 volt. I want you to make 1 volt. So this force would try to force 1 volt out here, and this voltmeter would try to measure that 1 volt, but it's not connected. It doesn't see anything. And so it feeds back to the voltage source, hey, there's not enough voltage out here. You must be dropping a lot in your test leads. So I'm going to raise the voltage up, raise the voltage up, raise the voltage up. Well, in the early days, we had no limits on that. So you'd tell it to make a volt, and it'd fly to the 210 volt rail. Okay? And, just because you forgot to connect the sense leads, right? We said, well, that's no good. So we came up with a concept we call auto sensing. So all the source measure units in here are auto sensing. There is no settings for you to turn sense on and off. And we came up with auto sensing very easy. We just tied a 100K ohm resistor across here and across here. Okay. So this is an infinite input impedance voltmeter, and it can easily handle 100K ohm in its sense lead. So if nothing is tied up here, then it senses it directly here through the 100K ohm. Hence, it doesn't fly off to Never Never Land. Okay. And, normally this series resistance is in the neighborhood of a few ohms. Compared to the 100K ohm, it's negligible. However, in 4-wire Van der Pol Hall effect measurements, sometimes we will have a bad contact or a high resistivity measurement, and then this 100K ohm sense lead resistor can become a significant part of our measurement. And so in that case, high resistance measurement, sometimes we want to use 2 instruments rather than trying to use the remote sense as a separate set of elements. Does that make sense? So here's an example. We call it Lab 1, where we're trying to measure a 500 milliohm resistor. So we come out here and we sweep the voltage from 0 to 100 millivolts. Okay? And that measures the current, and we plot it a point at a time. Okay? And we actually go and we do a line fit on this, and we extract 1.2 ohms. But we know this is a 500 milliohm resistor. Why do we get 1.2 ohms? Then we go out and we connect our remote sense leads and do the same thing again, sweep it up to 100 millivolts. This time when we line fit it, we get 500 milliohms. So the remote sense leads actually went out and said, I'm going to compensate for the amount of voltage that's on the sample. Actually, if we take the delta between these two, we get this line right here. That's the lead resistance of this sample. So you could manually do this measurement and manually go out and calculate it, but the remote sense a lot of times takes care of that for you. You know, I rarely use remote sense. If you're not 10 ohms or less in your impedance, if you're not at tens or even hundreds of milliamps, you don't need remote sense, and that's a lot of extra wires you have to connect up. Normally I don't use it, except for when I get down to less than 10 ohms or above 10 milliamps. So here's how the SMU connectors are set up. And I wanted to cover this because it's a little unique to this particular instrument. This is the rear panel of the instrument without the preamplifiers, which is what you have here. Right? We have 3 mini triax connectors. We have the top connector, which is called a sense low connector. We have the middle connector, which is the sense high connector. And then we have the force high connector. Okay. Down here we have a VGA connector, which is used to attach the optional remote preamplifier, which you don't have, you'll not be using that connector. So really all you need to do is connect to this force connector, which the center pin is the signal. It's a triax. The inner shield is a driven guard, which we'll talk about in a minute. And the outer shield is the common, which may or may not be earth ground, right? And then we have a high sense and a low sense. So normally you'll just connect this connector right here. One cable, one triax cable. Now, if you had the optional preamplifier, it's got two standard triaxes on the output, right? And that could be mounted on the rear or it could be mounted remotely if you want to get to really low currents. Now, we also have what's called a ground unit. So remember that all four of these source measure units like to work together. So you may remember the example that we started with the 4-terminal MOSFET. So that means all four force measure units have to know what the common reference point is for each of them. That common reference point is what we call our ground unit. We have a ground unit on the rear panel of the instrument, which has a force connector and a sense connector on the ground unit. All right. This force terminal is the common for all the source measure units. All source measure units are ultimately referenced to this force terminal. This sense terminal is not common to all the instruments. Well, it's sort of common in that it's got a 50 k ohm resistor to all the instruments. So this sense terminal gives you a pretty good low side sense on this measurement. But remember that this instrument had its own low sense on each source measure unit. So this low sense is directly connected to the voltmeter in the instrument. The common low sense on the ground unit is connected through a 50 k ohm. So it looks like this. There's a 50 k ohm from this sense to here, and a 50 k ohm to each of these source measure units. So in general, unless you're doing some unique application, you can just use the ground unit as the common for the instruments, and you can use the ground unit low sense as the voltmeter common for the instrument. So what does that mean? How do I actually connect something up? Right? Well, we have a very simple connection that we can take one triax cable, connect the center pin of the triax to one side of our device, which we'll arbitrarily call high, and we'll connect the shield of that to the low side. Now this shield is what I'm calling common. So the shield is the common for the instrument, but it's not necessarily earth ground. There's actually a small ground link in the back of the instrument. If the ground link is made, then all the commons of these are all at earth ground. If the ground link is taken out, then they're all floating. The whole instrument is floating from earth ground. Okay? So the current comes out of the force pin and comes back to the outer shield. The same would work with the preamplifier. The actual connection looks something like this. We have a force pin, which is surrounded by a driven guard, and then we have a common or a shield surrounding everything. All right. We're going to talk in more detail about guard, but the rule of the guard is never connect anything to the guard. Guards are there for a specific reason, and they're not to be connected to. So this really appears to be a one-wire measurement. But the truth is, whatever current you send out has got to come back somehow. And it's either going to come back through a controlled path like the shield of the triax cable, or it's going to find its way back through earth ground somewhere. It might go run around the building for a while and a few hundred ohms and a few hundred microhenries later wind up back at the instrument, right? But it's got to come back. Remember that you always need a completed current path on this. So here's how the common connection works on the SMUS. SMU1, force high through an ammeter, through a guard, and it's sitting on top of its voltage source, and it is tied to the force low of the ground unit. So all 4 SMUs are referenced to the force low of the ground unit, all right? That's the center pin of the force terminal in the ground unit. That's the reference. All the SMUs are referenced to that, right? So what if I wanted to do a full 4-wire Kelvin remote sense measurement? Well, what I would do is I would grab the SMU number 1 force line, attach it to my device. I would connect another cable to my SMU number 1 sense line and attach that to my device. And then I could attach the device to the ground unit force and sense lines back here on the ground unit, giving me a full measurement across that device. If I had 2 devices in parallel, I could take SMU number 2 and connect it to device number 2, and then reference it back to the same ground unit. Remember, the sense line is a high input impedance. It's going to actually sense the true voltage that's out here at these. So I can test these devices in parallel. So the point here is this. I've got a source and sense high on each source measure unit, and they can all use the ground unit as a common. If the optional preamp were connected, the same exact thing would apply from the preamp outputs. It's completely invisible to you as the user. Okay. Interlock connections. Now, you remember I told you this unit is capable of 210 volts. And that does hurt. I've grabbed it before. So we created a connection, little 3-pin connection on the back of this called an interlock. This is intended to be wired up to a test fixture or a probe station. When you open the door, what this interlock does is it directly shuts off the 200 volt power supply. All right? That's actually an OSHA rule. If you have an interlocked instrument, there is a relay in the 200 volt power supply. So when you open the interlock, it will shut off the 200 volt power supply. So if you don't have the interlock connected, which many analytical probe stations are wide open, they don't have an interlock, then this unit is limited to 20 volts. However, in software, you can go ahead and set it up that you override the interlock. And when you override the interlock, the instrument will ignore the fact that there's no interlock on there and will attempt to make voltage and can go up as high as 35 volts. But remember, the interlock itself hardwire shuts off the 200 volt power supply. So what is the result of this? Frequently, we will see people override the interlock. They'll go in on software and override it. They don't have an interlock on their probe station. Okay? But then they'll go and they'll program up a 100 volt sweep. And the 100 volt sweep will come up and hit 35 volts and clamp. Okay? Or maybe 36 volts. Actually, what it's hitting is the internal power supply rail of the op amp of the SMU. So, and they're going, why does this thing clamp? Well, it's because the interlock, which you've overridden in software, actually isn't made, so it actually doesn't have a 200 volt power supply. So if you want more than about 35 volts, you actually have to have the interlock connected to something. That's actually just a switch between pins 1 and pins 2 of this interlock connector. And just because you can take a safety pin and stick it in there, right? I'm not recommending that you do that, but you know, that would do it. And make sure you don't jumper pin number 3 because that's actually a 5 volt source. Okay,